experience the lesson in a, more real way. I'm also going to remember not only to do my attendance, but to do it on a different screen so that you can't go online and see like, oh, Kyle isn't here because he has some horribly embarrassing medical condition, and it like lists it on there.
I feel like we did this.
You did, but it's new. Everything old is new again. Here's the deal. The first 2 slides are going to be like, we've seen this. And then if by the third you've still seen it, then you can leave. But that won't happen. I do. But you're right. The first couple slides, I absolutely stole from my grade 11 note. Because I can.
I was trying to log into OneNote last night on my OneDrive program on my Mac, but I was typing in, it won't let me log in.
We'll take a look at it together. You can do it. It just can be a little bit of work, but we'll get there.
As it kept Microsoft technology.
Yeah, we'll make it work. I promise. Okay.
Well, I log in online. I can't log in.
Program, or did you open the program then go?
McGowan, I'll show you, okay? It's not so bad. Okay, could some sweet, kind, gentle, lovely human being hand these out for me? There we go. Thank you. I love that I have an overhead projector in this a lot. I'll say this though, I like it. I like it better than the whiteboard in as much as you can at least. Now this is really superior, but it's nice to face things. Okay, I'm gonna do my attendance. So I'm a responsible educator.
Y'all know that one fast.
I just want to have a good first week. Build up a bit of goodwill. Thank you very much. And then then not follow through on that. But who's missing? I don't see. Is Briar here? Briar's not here. Is Jessica here? Still not. Till tomorrow. Okay. Okay. You're not here tomorrow.
I'm not here tomorrow morning.
Okay. Good to know. Okay, so today, this whole unit is about quantum mechanics. So we're going to dive a lot deeper into how the atom works. So up till now, we've learned a theory of the atom, which has the nucleus made of protons and neutrons and electrons orbiting around it. We're going to start talking about the ways in which that's accurate and the ways in which it's inaccurate. Today's Tuesday, Thursday, and moving on. But we want to focus on how we got to here. And that's not something we spent a long time on in grade 11. So we talked about this guy Leucippus, right? This ancient Greek philosopher, and he theorized that if you took it in half and cut it in half and cut it in half and cut, eventually something. Can I just take a pause to say, I just taught this lesson. It's really weird feeling teaching the same lesson back to back, and I don't like it. I feel like it's going to take like 6 minutes to teach it to you because I'm just going to skip everything. Be like, I already said that. I did a student teaching block in a middle school in Niagara Falls, New York, where this teacher, Ida Bazzelli, amazing teacher, lovely, she taught the same science class 7 times a day. She taught grade 7 science just 7 times a day. And I don't know how she did it, because I would have gotten to about the 3rd time and then just like turn the lights out and huddled in the corner and like, but I had to do it, obviously. I was there for months. And by the 7th period, you'd be done in like 4 minutes. You'd be like, what didn't I say? Anyway, it was not the life for me. Anyway, so yeah, this guy Leucippus said that if we just kept cutting it, eventually you wouldn't be able to cut it anymore. Eventually, you'd hit something indivisible. Not unlike if you were at home and you started taking your Legos apart and taking them apart and taking them apart. You can keep doing that until eventually until you can't, until you just got a big pile of bricks, and those bricks won't break apart. And this is Leucippus's idea. He says that if that's true for a brick wall, if that's true for Lego, it must be true for everything. That if you keep breaking it down, eventually you're going to hit something that makes you stop. And he said that what remained at this type must be this indivisible particle. You know, these small little building blocks that everything's made of. And he gives them a name. Actually, he didn't. I lied. This guy Democritus gives it a name. He calls it atomism. Sorry? That's kind of how that works. You also are like way back there in Narnia. Like, there's seating available up here. Anyway, I'll leave that to you people to fight about. So he turns this into an idea called atomism from this Greek word atomon. Atomon. And I pulled out my wife's Greek lexicon, and it told me that atomon in the Sophoclean language means uncut or unmown, and in Platonic thinking it means that which cannot be cut, something that's indivisible. And then by New Testament, it comes to mean a moment. But this idea of something that cannot be cut, can't be destroyed. That's what our word atom means in its Greek origins. Now we know, by the way, that that's a bit of an oversimplification, isn't it? I mean, a lot of our power in Ontario comes from nuclear power, which is power that comes from breaking atoms apart. So we know that this isn't quite right, but still it's quite a step for a philosopher to come up with this with nothing but a thought experiment. And there they are. As I said last year, if I were throwing a party, I know who I'd invite. He's a fun-looking guy. Like, they're both bearded old gray men, but one of them looks like he's probably got some stories to tell. Anyway, that's just, and I might be totally wrong. Like, but anyway, that's Democritus on the right. So, and why wouldn't he be happy? He put his name on somebody else's idea. Anyway, so there's a problem, which is, had you ever heard of, before taking chemistry, Leucippus or Democritus? No. Who are they? The nobody. The nobody because you probably... What? Don't make fun of her.
Aristotle.
There you go.
And I didn't know how to say it.
But this is good, because I was going to say that. This actually is a perfect segue, because Aristotle is probably somebody that you have heard of. Aristotle. Okay, so the problem comes from somebody you probably have heard of, who is in his own right a brilliant philosopher and really somebody who forms the foundations of a lot of scientific thinking. One of the first people we have on record doing dissections. Somebody who contributed a lot to thought and to our understanding of the world around us. But still, on one thing, he got it horribly wrong. This guy, Aristotle, whom everyone has heard of, actually believed the opposite. He believed that matter was continuous. He believed that water, and this is probably how most of us thought of these things before we started thinking about them, we think of water as just water. And he said if you zoomed in 1,000,000 times, it would still look like water. If you zoomed in 10 million times, it wouldn't look like water. And when you stop and think about it, that kind of makes sense. There's no reason to think that as you get smaller and smaller, water all of a sudden becomes solid particles. Right? His intuition is good, but his outcome is wrong. But he believes that all things are continuous in nature. And he exemplifies this as air. He says, look, air is just air. It doesn't matter how small you get, it's still just air. It's this elemental thing. By the way, he didn't believe, despite what some people think, that everything is made of fire, water, air, and earth. He just said that those were good examples of this principle, of the continuous nature of matter. Now, as a result of this idea, the idea of atoms basically disappears. And not for a little bit either. For about 2,000 years. For about 2,000 years, nobody really thinks about this idea of atoms because it's been eclipsed by this other idea. And keeping in mind that we didn't have the techniques to look at these things at the time. All you could do were thought experiments. All you could do was look at the world around you and try to draw conclusions. But it takes a series of discoveries in the 18th and 19th centuries to really rediscover the atom. This is where the note diverges from the one you saw in grade 11. So I want to draw your attention now to a guy named John Dalton. I like John Dalton's glasses. I think they look nice. When I was a kid, I always wanted glasses, and I didn't need them. And then the day I needed glasses, I never wore them again. So shows the grass is always greener on the other side, right? Moving on. So John Dalton performed an experiment that you guys have seen done, electrolysis. Do you remember electrolysis experiment? I had the big orange contraption over there. All right, what happened when we conducted electrolysis on water? What do we see?
It's separated into hydrogen and oxygen.
Good. So the first thing he sees is something that already proves this Aristotelian idea wrong, right? Aristotle says that water is continuous, that it's one of the elements of nature. And Dalton finds that if you put a little bit of electricity through it, and by the way, a little bit, you can do it with a 9-volt battery, and it works just fine. If you put a little bit of electricity through it, it's not elemental at all. It breaks apart. It breaks apart into two different things. So already he's shown that Aristotle's idea is lacking in something. But that's not all he finds. Do you remember when we looked at those tubes? What else could we see? Someone else. You were in the front row. Yes, we saw oxygen and hydrogen. No, they actually came out separated, right? Because crazy as it is, the oxygen collects at the one terminal, the hydrogen collects at the other terminal. Pretty cool. What else do you see? Is it equal?
Not equal, like it's the same ratio.
Good, it's a ratio. He found that no matter what he did, he got, how much? What is the ratio? 2 to 1 what? Yeah, 2 hydrogen to 1 oxygen. Now, to you that makes sense, because before you knew what atoms were, you knew that water was H2O, right? You just heard that your whole life, right? On like some bad Gatorade commercial, they mentioned H2O with like loud guitars playing in the background. You're like, I want Gatorade. But so to you, that makes perfect sense, right? We didn't really have to think about it. But imagine having thought your whole life, having come from a school of thought in which they believed that water was this indivisible thing, and they find that when you put an electric charge to it, you actually get 2 smaller things and known things, right? Because he knew how to test these. He got gases, and he knows how to test oxygen. What's the test for oxygen gas? Do you guys remember? Somebody said fire. The test is fire. Let me ask. That's fair. That's fair. Well, has anyone heard of the Apollo 1 disaster? Right? In the Apollo 1 disaster, they were pumping oxygen into the cabin, and so much so that with enough oxygen in the cabin, even though everything in the cabin was flame retardant, nothing was flammable, that wasn't true once there was enough oxygen. So even though something like the Velcro they were using was flame retardant at normal atmospheric oxygen, which is pretty low percent. What's oxygen percentage in the atmosphere, like 22% or something? 21, yeah. They found that when you pump 100% oxygen in, stuff just ignited, which is awful, right? But the test for oxygen, if you remember in grade 9, is you take a splint and you blow it out. So it's not in flames. And if you put it into a tube full of oxygen, what happens? It reignites. That's the oxygen test. So he's able to test the one gas and sees that it's oxygen. He tests the other gas and finds it's hydrogen. What's the test for that? Nope. If it goes out, there's something inert. Maybe CO2, maybe nitrogen. What happens if you put a lit splint in a thing full of hydrogen? It blows up. Yes, absolutely. Yes, correct. You get that pop, right? It would have been good for the Hindenburg if the hydrogen had put it out, but that's unfortunately not how it works. That was kind of dark. That was darker than I meant it to be. Those were 2 really dark examples. Wow. Don't know what that says about me as a person, but okay. So he tests these two things, and he finds that not only does he get hydrogen and oxygen, but he gets them in these fixed proportions. No matter what he does, he gets twice as much hydrogen as he does oxygen. And from this he concludes that no matter where you go, every particle of water must be the same. That's his first conclusion. All this water must be the same. Because whether he took it out of the Thames River, or the Atlantic Ocean, or some stagnant pond, or a fountain in London, it all gave him the same result, which was it always gave him twice as much hydrogen as oxygen. So he says, okay, every particle of water must be the same. Likewise, it's made up of 2 hydrogens and 1 oxygen stuck together. Because when I break it all apart, I get 2 hydrogens for every 1 oxygen and nothing else. And so he comes up with this idea of fixed proportions. And you can go ahead and underline that or highlight it or put a square around it. You could put a hashtag in front of it if you're feeling very trendy. You could, I don't know, you could put quotation marks around it. I used to have a boss who would put quotation marks around words that made no sense to have quotation marks put around them in memos. And it used to be very distracting. Anyway. So here's Dalton's theory of the atom then. Dalton says that everything's made of atoms. Everything in the world must be made of little individual particles, like the hydrogen and the oxygen. And he can test for this, of course. You've done decomposition reactions. He starts doing decomposition reactions. He starts taking things and finding that if you add electricity or if you add heat, you can get things to break apart. But there's certain things that once you get them, they won't break apart. For oxygen, I can't make something smaller from it. I can make something I can get to react the other way, but I could never break it apart and get it to be smaller. Once I get hydrogen, I can't break it apart and get something smaller. Once we burn something and get the carbon out of it, like charcoal, I can't break that down and get something smaller from it. Yeah, I can burn it, but I end up with CO2, which is something bigger. So carbon must be one of those indivisible things. And he and other scientists start finding all of these indivisible atoms that you just can't get smaller than. And he says, everything must be made of this stuff put together. Second thing, all atoms of a given element must be identical. A carbon atom must be a carbon atom must be a carbon atom. They must all be the same. They must all weigh the same. They must all have the same chemical properties, physical properties. Carbon is carbon is carbon. Is that true, by the way?
No.
It's almost true, but it's not quite right. What do we know about mass?
Slightly.
Yeah, it can be different slightly, or even pretty substantially, because of isotopes, which is where the same 2 carbon atoms have to have the same, we know now, number of protons, but they may have different mass because they may have different number of neutrons. So we know that now. He didn't know that then. So he says they must all be the same. I just don't want you to like take this from the exam and be like, well, it said in the note on the first day that they're all the same. And they said compounds must be formed by putting 2 or more of these things together. So, you know, in Lego world, all things are made of Lego, but when you start putting them together, that's how you make more complicated things. Start sticking them together. Playing with Lego would be very boring if you weren't allowed to put them together. This is why Lego is the best kid's toy ever, and wooden blocks less so. Yeah. Right? And even then, the wooden blocks are only really fun when you still put them together and make like towers or something. So compounds are formed when we put them together. And the last thing he says is, all a chemical reaction is rearranging these atoms. All the chemical reaction is taking apart the Legos and putting them together in new and exciting ways. Ideally, taking your sister's castle apart and turning it into your own castle, and then she pulls your hair for a while. That's all a chemical reaction is. It's just your sister beating you up. I like to exercise some of my childhood demons in the class. Yeah. By the way, he doesn't really have a sense of what these things look like. He imagines that they're little spheres, little billiard balls. And he figures they have to have a way to stick together, so he imagines that they have little hooks on them. But he's not saying that's what they really look like. That's kind of a useful model, a way to think about them. But he understands that they don't really know what they look like. And from there, we enter somebody who knows a thing or two about looking, J.J. Thompson. I dream of having a mustache like that one day. I've always said that I want my teaching, my last year, I'm just gonna get one of those twirly mustaches, and then just make all the tests really hard, and just sit at the front and go, yes, try question 11. I'm gonna get out. Just that'll be it. Anyway, so there you go. We got J.J. Thompson, who looks like he's borrowed Dalton's glasses, actually. And he performs an experiment that I'm actually going to demonstrate for you tomorrow. We're going to look at tomorrow. Tomorrow we're going to kind of recreate some of these experiments.
Oh, is this the water bottle one?
Nope. No, this one is in something called Crookes 2. And now let's keep in mind that in the time that has passed, they've started discovering all of these atoms. All right? So we said they start decomposing things and they find all these things that it can't decompose. And a lot of time has passed. They've learned a lot. All right? By this time, the periodic table is being built. All right? They start to understand what the mass of these different atoms are. And they've even done some basic calculations to find their radius. So they know how big these things are. They know how much they weigh. And along comes a guy named Crook, who invents this tube. And this has been around for a while. But it's a vacuum tube. It's just a tube that has had all the air evacuated from it. So there's no air in here. Vacuum, so it's under pressure. So the glass needs to be rigid to hold it out. If this were made of like the material of a plastic water bottle, it would crunch it. Right? This is a vacuum tube, no air. But the glass is good and rigid, so it holds it in place until I drop it. And then they just have two electrodes. An electrode here and an electrode there. And what Crook found, and then they've coated the glass with phosphorus, which is what they used to put on TV screens. And what he discovered is that if you put electricity through this, you get this green ray, like that. And it's a little ray, presumably of light, right? This visible ray of light. That's kind of a cool thing, and you can see it there. And that seems to make perfect sense. J.J. Thompson comes along and holds a magnet up to this thing. Now, does a magnet move light? No. All right, you can test this yourself. You can go home. Turn on a flashlight. You can hold a magnet near it. The light will not bend. I promise. Glass will bend light. Glass will refract it. A magnet does not bend light. Except at super cooling temperatures like that. But that's neither here nor there. For the purposes of this class, a magnet will not bend light. But when J.J. Thompson holds a magnet up to this device, and tomorrow when you hold a magnet up to that one, the ray of light bends. So what does he determine from that? What would you determine from that? Okay, electromagnetism is a word. It's got like two words. It's got like electricity, which he used, and a magnet, which he used, so it's a good word. He didn't actually. You're right that they are. Like, you're completely right. That's not what he determined. He knew, look, he knew what kind of stuff does a magnet move. I mean, metals, magnetic stuff, but it all is stuff, isn't it? It's all things. Now, is light stuff? Is light made of particles flying through? Not really. I mean, massless particles, yeah, photons. And that's usually where they are. They think of light as a ray of energy, which it is, by the way. It's both. But it doesn't have mass. It isn't stuff. So he draws the conclusion that if a magnet is moving this, it's got to weigh something, which is true. For a magnet to move something, it has to weigh something. That's how it works, because they had calculations for how magnets worked. And all of those calculations involve knowing the mass of the thing that's being moved. These people weren't stupid. I'd love to show you the calculations that come from this, because they're pages and pages and pages. It's very complex math, really, really intense algebra going on. But he determines not just that these things must have mass, but he can actually calculate, based on how much the magnet moves them, both their mass and their speed. Pretty crazy, right? That's some pretty intense math. But he's able, using different size magnets, different power magnets, changing all the variables, he's able to sit down and figure out how heavy these things are, and how fast they're moving. He finds them moving very fast. And what does he find out about how heavy they are? Yeah, they're really light. All right, so like I said, this time they've identified all the atoms, and they think that the smallest thing in the universe is hydrogen. It's the smallest atom they've found, right? And he finds something that's 2,000 times lighter than that. Yeah, because the other thing he finds is that it doesn't just move with a magnet. Remember in grade 9 when you like took the ebonite rod and like rubbed it on rabbit fur and put a static charge on it? You did that, I'm sure? He discovers that if you take a charged rod like that and put it near, if it's a positively charged rod, this ray will move towards it. If it's a negatively charged rod, the ray will move away from it. So now he knows it has mass, but he also knows that it has charge. Specifically, it has a negative charge. Good. So J.J. Thomson has discovered electricity. No, it was around. They knew about electricity, but he's discovered a small particle that's 2,000 times lighter than hydrogen and has a negative charge. The electron, which you'd already said. He's discovered the electron. I'm going to put some of those words up so you can like fill them in. So he does this, and he determines that there's this tiny little negatively charged thing. But he also knows that the glass was in a vacuum. So there weren't any particles in there to start with. So he knows the particles must come out of, they must come out of the anode and the cathode. They must come out of those little metal terminals. In other words, they must come out of the metal atoms. Because if you take the metal away, if you just take the tube and hold the electricity on each side, push it up against, you won't get it. There has to be some atoms for these particles to come out of. So he determines that these must be part of the atom, but he knows that atoms aren't negatively charged. He knows that if I touch this, I'm not getting shocked. No charge. So if there's a negatively charged particle, there must also be a positive one. Good. And this is all what we've just said. He said that the small, the negatively charged, and because atoms on the whole are neutral, there must also be a positively charged thing in the atom. Copy the keywords. It's weird, I don't do a lot of lectures, so I wasn't sure if I was going to give you notes at all, and I thought, I'll give you fill in the blanks. And now I feel like a grade 9 teacher watching you fill in the blanks. Ever seen Ferris Bueller's Day Off?
Yeah.
I had seen it obviously when I was a kid, and I saw it for the first time in like 25 years this year. And the scene where Ben Stein is teaching, he's teaching history, and he's going like, and that was the start of the great, anyone, the great, blank, yeah, depression, that's right. All right, and of course, this was called by President George W. Bush, VOO, blank, VOO, rhymes with who, that's right, voodoo economics. I thought, oh my God, that's unbearable. Anyway. Whatever.
See, we hear more of like the Charlie Brown, like.
Oh, good. Thanks, Kyle. That's what I'm going to hear when I read your paper next time. So all of this leads him to come up with this idea. Oh, that's the same notes. He comes up with the idea that these little negatively charged particles, which he calls corpuscles, this is corpuscular theory, we use electron now, but he imagines that they must be little tiny negatively charged particles stuck in the whole thing, which is positive because remember, he knows the radius of the atoms. So he knows they're big. So he thinks, wow, if there's these little tiny negatively charged things, and I know the atom is big, the positively thing must be this kind of big positive charge like this, and stuck in it must be all these negatively charged particles. Makes sense, right? And so this is called, you'll hear people say that he called this the plum pudding model. He didn't ever. He didn't say that. Newspapers said that when trying to summarize his findings. But the idea is that it's like a blueberry muffin, or it's like a plum pudding, which is that the atom is neutrally charged. You have this large space with most of the mass, and it's positively charged. And then these tiny little, like chocolate chips of negative electricity thrown in there. Oh, sorry. And yeah, so that's what they call the plum pudding model. And you can draw that if you want. It should take about 3 seconds. I'll give you 8. Now, the other thing is this. To read a chemistry textbook, you would think that like 5 people discovered everything, because we mentioned like this handful of people. Oh, and by the way, they're all white men, just if you're wondering.
Oh, yeah.
There's like 6 white guys who've just solved the universe, and everyone else was just being lazy, I guess, at the time. All you women and men who aren't white. But in fact, that's actually not true. And sadly, I pulled out our textbook thinking like, hey, no, yeah, it's all white men. So I thought, like, just to show, there are, and to be clear, most of the big discoveries did come from white men because white men had opportunity that everyone else did not at that time. But just as a case in point, the next guy is one I find really interesting, a guy named Hantaro Nagako. But in 1904, this fellow suggested that the electrons might actually, the negative particles, might actually surround the central positive mass, kind of like Saturn's rings surround that planet. Sounds kind of familiar, doesn't it? And this was based on his finding that they couldn't penetrate one another. The negatively charged particles couldn't be inside the positive charged particle because then they could never escape. He'd done them, and again, he's not just throwing this out of thin air, he'd done the calculations, right? He said if you have these tiny little particles with a negative charge and they're inside of a positive charge, nothing is going to induce them to get out of there. Because why would they? They're attracted to positive charge, and where they are surrounded by positive charges. So he does some math that says they can't be inside, they must surround it. Now he still assumes that the positive makes up the bulk of the mass and the size, but he says that these things can't be embedded in it. And while not entirely correct, this is an example of one model. And by the way, this is one other guy. There's hundreds and thousands of people doing this, doing their own calculations, having their own findings. So this idea that science happened by 5 people being really smart is really missing the point. It's important to remember that, like, when Darwin discovered evolution, somebody on the other side of the world was writing the exact same stuff at the exact same time with no relation between them, because technology and science had led to a place where that finding was kind of inevitable. Likewise, Alexander Graham Bell invented the telephone. So did Elijah Gray. They filed for a patent on the same day. They lived on opposite ends of the country. Their labs had nothing to do with one another. They didn't know each other. They developed the same technology. They filed for a patent on the same day. Bell's patent went in 3 hours earlier, right? You imagine? Imagine the difference in their lives. You imagine how pissed off you would be if you'd invented the telephone and somebody else patented it 3 hours before you. But keep that in mind. Science doesn't happen because 5 people are really bright. It's constantly happening, and there's thousands and hundreds of, and today, literally tens of millions of people engaging in science every day in all different fields, all different skills, bringing all different skill sets and understandings. People who are artistic, people who are creative, people who love to build things, people who are great at math, people who are terrible at math, all doing science, all contributing. And so while you get this like greatest hits presentation in chemistry, don't think that that's how it works, because it's the exact opposite of that. It is not individual efforts. It couldn't be less individual efforts. So this is just one example of that. One example of one guy's tiny little discovery in theory, which at the time is insignificant, but builds to this mounting knowledge and this mounting understanding of how science works. But this is his basic idea. Starting to look a little more familiar, isn't it? You don't need to draw that. It's not how it works. All right, but this leads us to one of the big important experiments by 2 men. Geiger, sound familiar? Yeah. And Marsden, all right? And these guys were students at the time. They were postdoctoral students, and they were working for a scientist named Ernest Rutherford. Usually you will hear this experiment called the Rutherford experiment. Rutherford didn't touch it. He was just the guy they worked for. But that's also how science works. Your boss will steal your credit. Make no mistake about it. I mean, whatever. Anyway, so Geiger and Marsden, and they did an experiment where they built They built a box that had inside it a piece of radium. Now, what's radium? It's an element. It's radioactive. Sort of Marie Curie. Yeah, she discovered radioactivity, right? So it has a piece of radium, and it releases these particles, these alpha particles, in all directions. But there's this tiny little gap in this lead box, which lets the particles out only in one direction. So you can make like a fine pointed stream of this stuff. Makes sense, right? No different than what we do with light. Right? We just put a little aperture like this, and now you've got a straight light. Straight beam of light. So they fire this stream of alpha particles, and they put in front of it a little piece of gold leaf. All right, and gold can be pressed. It's very malleable. Remember that word? Grade 9 science? Ductility, malleability, yeah. Okay. It can be put into a very, very, very thin sheet. A sheet so thin it's just a few atoms thick. Right? Very, 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 very thin, very fine. So they fire this through, and they do some calculations. And remember, they're thinking of the atom in Rutherfordian terms, or in J.J. Thomson's terms. So they're imagining that it is this muffin with little electrons thrown in. And again, they've done the math. They know how big this thing is, and they know how much it weighs. They also know how big these alpha particles are, and they're tiny. We now know, by the way, that an alpha particle is a helium nucleus. Two protons, two neutrons stuck together. So it's quite small, and it's really dense. But they didn't know that at the time. They just knew it was this particle that was really heavy, but very, very tiny. Because think, we now know the nucleus is like just 1/100 millionth of the size of the atom. The atom is huge, the nucleus is tiny. They think of all the atoms as the size of the whole atom. So they think that the weight of that gold atom is distributed through this whole thing. But now they have this tiny little particle, really heavy. Now I want you to imagine that we have something that's really big, but has its weight all spread out. And then we take something that weighs just as much, but is tiny like this, and we shoot it at really high speed into this. What's going to happen? That's right. It's like a bullet into some soft object. It should go straight through. And they do the math, and they see that yes, based on knowing how big the atom is, this should go straight through. And they actually calculated, and they knew that there should be some deflection. And they said basically it should be about plus or minus 1 degree. Very, very small deflection. And again, they've done the math. So they've done the math and determined that these particles should be able to fire directly through the foil with minimal deflection because of Thomson's model. This idea that the atom has its weight evenly distributed. Oh, so they were expecting to see this. They were expecting to fire the alpha particles, have them go through the gold foil, and to hit this detector, which is just a phosphorus ray. All right? And the nice thing about the phosphorus is when it gets hit by a high energy particle, it glows. So they thought that they should shoot this, they should see a big glowing spot right there. And this would confirm. And they were testing, by the way. They weren't looking to discover something new. They were trying to determine if their calculations were right and if the small deflection is indeed the deflection they would see. And this is what they thought would happen, which is that those particles should be able to hit the atom, and no matter where they hit, they should be able to travel pretty much straight through. Small little deflection. Since we're talking about it here, did they see that? No, there wouldn't be much sense talking about it if they found it. What did they find? Well, they found that the vast majority of alpha particles pass through with no deflection whatsoever. And that's actually not what they were expecting either. They expected to see some deflection. Most of them, straight through. No interference whatsoever. But every once in a while, there would be a deflection, but it wasn't little. 150 degrees. They'd ricochet all over the place. So they would have this set up, and they'd have little bursts happening all over the place. So 150 degrees, remember, in either direction. From a 360-degree circle, you're talking about 300 degrees of deflection. Big, 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 big. And that meant, well, what did it mean? You see that, what's it mean to you?
Not all distributed across one floor.
Yeah, that weight can't be distributed. The weight's distributed, the alpha particle has enough motion to rip right through it, and we know that's true. But it didn't rip right through it. It either doesn't touch it at all and just goes straight through, or it hits it and bounces like crazy all over the place. So that weight can't be distributed. If you fire your bullet and it bounces back at you, it didn't hit foam rubber. Hit something else, right? You know that. Doesn't matter how many times you do it, the foam rubber is not going to shoot the bullet back at you. It has to hit something dense, doesn't it? So those alpha particles bounce back and have to hit something dense. So he goes, well, all that mass must actually be condensed. Now that also explains the vast majority going straight through. Because if all that mass is condensed, most of those alpha particles are going right through nothing. The reason they're not even deflecting a little is because they're going through empty space. My mother always said that I had an empty head. Well, she's right. Like 99.99999% true. Overwhelmingly, everything you touch around you is mostly empty space. Almost completely empty space. But the mass it does have is condensed into these small little nuclei. And that is what this experiment proves is evident. So what they see is this, all right? They see that most of them travel straight through, but when it does deflect, it deflects big because it struck the dense nucleus of the atom. These are kind of the observed results that you see there. You can sketch that if you want. The note is online. You'll be able to see it. And Ernest Rutherford formalized these findings, and he built a model of the atom in which the nucleus is at the center of the atom, and it contains the vast majority of the atom's weight. There should be an apostrophe on that. -1 for me. Of course, you all know where to put it. We'll correct it. But the electrons discovered by Thomson, remember, were assumed to be orbiting around. Because now we really knew that they're not going to be stuck in that massive mass of positive charges and be allowed to escape. So we know that they orbit around. And that is almost all of the way to your grade 11 understanding of the atom, which we are now going to expand upon in the next couple of days. I do want you to know all this, by the way. You should be able to speak confidently about each of these experiments, how the experiment was conducted, and how it contributed to our understanding of how the atom works. These are seminal experiments. They're important. Tomorrow, we're going to recreate a couple. So tomorrow at the bench, I'm going to have Crook's tube set up. I'm going to keep you guys at a bit of a distance because it releases some low power X-rays. But they don't have any real penetrating power. They're very low power. You put 5,000 volts to that to keep not to produce a very, very low power X-rays. It would take you get 25,000 volts for the after that. All the same, you guys at a bit of a distance. I'll do the radiation exposure thing. But we'll show you the experiments you did. My heart's going to get me long before anything else does. So we're good. Which I mean my cold, cold heart. So you'll do that. And then your other experiment tomorrow, I'm going to have you guys build your own electrolysis tonight. And not using the big apparatus I had, but I'm going to have you use kind of all the equipment that's in the lab that you may want. I'm going to have the connects out. I'm also going to bring kind of a grab bag of random stuff, some Tupperwares, some elastic bands, some plasticine. So that's going to be kind of your little first mini lab tomorrow. It's just kind of a fun experiment to get up on our feet. For now, today and yesterday were painfully dull, and most of the days to follow will be painfully dull. So I want to do a bait and switch by having like a day that's kind of fun. But so what I want you to do for homework today is familiarize yourself with what an electrolysis setup is and why it works. How and why. What are the components of an electrolysis rig and why does it work? All right, because tomorrow you're going to have to build one from equipment that was not necessarily meant. So here's some questions you might ask. If I have to put electricity through water to make it break apart, what kind of electricity do I need? Because I'm going to have to get it out of this room. right? Like, will a battery do it? What kind of battery? How do I have to wire it? What am I connecting it to? Can I use the power supplies that we have? Do I need to, a battery will do it, but do I need to do some kind of circuit, like a voltage step up? Who knows, right? That's what you are going to do. So tomorrow you're going to build a little setup and then answer some questions. Okay? That make sense? All right. I just want to take 2 minutes to remind you, because again, most of you didn't have me last semester, I know. And so most of you haven't necessarily seen how I'm structuring my note-taking and all that jazz now.